Okay. Hi, my name is Rachel. Today I'll be talking about binary error correcting codes with minimal noiseless feedback. This is joint work with Meghal and Venkat, who are both at UC Berkeley. So I guess to start, I should probably tell you two things, like one, what are error correcting codes, and two, what is feedback? So let's start with error correcting codes. So in an error correcting code, the goal is suppose Alice has a message that she wants to send to Bob. If there's no noise, she could just send over her input exactly. But what if the channel is noisy? So in particular, suppose that some of the communicated bits are corrupted. So for instance, if Alice was trying to send 00101 to Bob, but the second zero is corrupted to a 1, Bob might not be able to figure out that she intended to send 00101. So the question is, can Bob still learn X if Eve corrupts some of the communicated bits? And turns out the answer is yes, and this is done with something called an error correcting code. So the idea is instead of Alice just sending over X to Bob, where X is her input, she can instead send an encoding of her input X, which we denote by ECC of X, which will have some distance properties that every two code words are pretty far apart, so that even if a few corruptions occur, Bob can still round to the nearest code word and figure out what message she intended to send. Okay, the next thing I want to talk about is feedback. So in the world, there's a lot of processes which incorporate feedback. In general sense, feedback is the notion of sort of sending back information to someone who is trying to send information out into the world. So maybe let me give a few examples to illustrate what I mean by this. So one example is control systems. So suppose that you are sending controls out to robot or another machine to command to do something, right? Roll on the floor, move forward, whatever. But then using what you see, using whether or not you see the robot actually moving forward, you can then adjust your next command to tell it to turn right next or something. So in particular, it's seeing what the robot does, getting a sense for what it's doing will allow you to make decisions for what to tell it to do in the future. Another example is a satellite. So suppose it's a satellite very far away from Earth, is trying to send pictures, information back to Earth, but this information is very noisy. But suppose on the other hand, you have a very secure communication channel to the satellite. So you can actually tell it hey, I didn't, receive the pictures or the information you tried to send me. Can you send me again? And that would then inform the satellite could then choose to send next. So it could choose, for instance, to repeat the information it's already sent. Okay. And so I guess the main point I wanted to convey is this feedback is often used to sort of inform what the information you're sending next is. Okay, so now let's talk about error correcting codes and feedback together, because that's the topic of our talk today. So in 1956, Shannon asked the following question: can feedback be used to improve error correcting codes? And unfortunately, it turns out the answer is no, at least not in terms of rate, which is communication efficiency. But on the other hand, Berkeley showed a positive result in 1964, which is that feedback can actually improve the resilience to error. In a sense, this sort of makes sense, right? If there's a lot of errors, you can sort of ask a question asking hey, can you clarify which, where the errors happened? Or maybe can you tell me a bit more information about the specific confusion I have? Okay, so let's talk a little bit more about this result. So, yeah, so in a standard error correcting code, this is a one-way communication. Bob is providing no feedback to Alice. Alice is just sending a one-way communication, that's it. It turns out that for binary codes, the guarantee is that as long as less than 1/4 of Alice's bits are corrupted, Bob is guaranteed to learn X. And 1/4 is optimal, so you can do no better than 1/4 is error resilience for just standard error correcting codes. On the other hand, in error correcting codes with feedback, the model is as follows. So every time Alice sends a bit to Bob, Bob can send some feedback back to Alice, telling her, what he's received, any confusions he's had. The important part is that Bob's feedback is noiseless. So it can never be corrupted. Alice is guaranteed to receive it correctly, and therefore she'll always know sort of Bob's state like for instance, Bob can just send Alice exactly what he received. So now Alice knows exactly what he received and can tailor her next message to send precisely the piece of information that he needs to hear. I also want to say that this feedback is does not contribute towards like the error resilience we calculate. So in particular, the adversary is given a corruption budget as a fraction of Alice's forward messages, and only Alice's forward messages, and she's only allowed to corrupt Alice's forward messages. So in this setting, it turns out that Berkeley's result shows the following. Oops, I don't know what just happened. Okay, as long as less than 1/3 of Alice's bits are corrupted, then Bob is guaranteed to learn X. So we see that without this feedback, you're only guaranteed 1/4 error resilience, but with feedback, the error resilience goes up to 1/3. Again, this sort of makes sense because Bob can ask Alice precisely for what he needs to hear to figure out what X is. Okay, so maybe let's talk a bit more about this result. So traditionally, when people study error correcting codes with feedback, Bob's feedback is continuous, which means that he sends feedback after every bit that Alice sends. So in particular, if Alice is trying to communicate X, which is k bits long, this means that Bob will have to send k rounds of feedback, but also more importantly, k bits of feedback. Because Alice has to send at least k bits to communicate X at all, and Bob is sending feedback after each of these bits. But in the real world, communication interaction is expensive. Guaranteed noiseless feedback, ensuring the channel will actually give you this noiselessness, is also expensive. And so the question we asked today is the following. So our main question is, how much feedback do we actually need? Do we actually need k rounds and k bits of feedback, or can we do better than this? Okay, so here are our results. So the first theorem is as follows. There exists an error correcting code with feedback where Bob only sends log k bits of feedback over constantly many rounds. And this is resilient to the 1/3, it has 1/3 error resilience, which matches the previous result by Berkeley, which has k rounds and k bits of feedback. And our second result is the following. This is tight. So in particular, we show that if Bob sends less than log k bits of feedback, then there's an attack corrupting only 1/4 of Alice's bits so that Bob cannot determine X. So in other words, if Bob only sends less than log k bits of feedback, then Alice's best strategy is essentially to send a normal error correcting code. Okay, so that's our results. For the remainder of this talk, I wanted to focus on theorem 1 and give you a sense for how this is done. So to talk about our construction, it'll be important to introduce a sort of alternative version of viewing error correcting codes with feedback. And this is called the coin game. So in the coin game, there's a bunch of coins. They each correspond to a possible input that Alice has. So if Alice's possible inputs have k options, then there are k coins. And they're placed on the number line, and its position on the number line is precisely the number of corruptions witnessed if Alice actually had that input, the coin as her input. So for instance, at the beginning of the protocol, no messages have been sent. There can't have been any corruptions witnessed. So all the coins are at position 0. As the game goes on, so some coins might increase their positions based on what Bob has received and what Alice was supposed to send if she had that coin. So for instance, if in the case that Alice has a coin 101, she's supposed to send 0 in round 1, but Bob actually receives the 0. Coin 101 will be at time step 1 at the position 1 also. So in particular, okay, so these are all started at 0. After one time step, some of the coins might move up to 1 because the message that Bob received didn't really match what Alice was supposed to send. And another time step, some more coins move up, and so on. And okay, so let's talk about the size of the board. The size of the board is like the corruption limit. So like how many corruptions we hope to fend against. So in this case, it's going to be the length of the protocol over 3, because that's our sort of target error resilience. And so in particular, it's important to notice that like as long as the coin is on the board, it's like a valid possible candidate for what Alice could have had, because that means that the adversary hasn't actually corrupted more than n over 3 bits in order to, if Alice actually had that message. And so the important point is the adversary's goal is to keep at least 2 coins on the board by the end of the protocol, because that means that both coins are valid candidates for what Alice could have had. On the other hand, Alice and Bob's goal is to design a protocol that this cannot be the case, so that so all but 1 coins have to fall off the board by the end of the protocol. So with this in mind, I want to talk about 2 strategies. The first strategy that is just like a standard one, just like standard error correcting codes. So in this strategy, Alice is going to send just ECC of X is going to be n bits long. And let's see what happens. So this is property of error correcting codes called list decoding. And essentially this decoding says that, all except for constantly many coins will move like at least n over 2 roughly. And like, maybe let me rephrase that for those of you who are more familiar with just error correcting code terminology. This means that like, if you want to decode within like n over 2 minus epsilon radius, there's only like O of 1 coins within that radius. Okay, and so pictorially, what this means is that by the end of the protocol, basically all but a few coins will have fallen off the board. And in particular, there's actually only like a very few number of coins which are less than n over 3 at the end of the protocol. So this is actually like a pretty good strategy, except for the fact that you can actually distinguish between these like, maybe 4 coins that you have left. Yeah, and so I guess like, so I guess this is like, so error correcting codes is a pretty good strategy for most coins, but isn't doing so well on just a few. And so the goal in like error correcting codes feedback, you want to actually separate these few early coins. Yeah, and so this is precisely what is done in constructions of error correcting codes feedback that achieve 1/3 error resilience. One example of such a protocol is a Spencer-Winkler protocol. So let me describe this protocol for you. So in this protocol, after every bit that Alice sends, Bob is going to send feedback telling exactly what he received, so that Alice knows at every point in time exactly what sequence of bits Bob has and knows his state exactly. So suppose this is a configuration of coins after some time step. What Alice is going to do is she is going to order all the possible inputs by their position on the number line. And then she's going to tell Bob whether her input is one of the odd labeled coins or an even labeled coin. Okay, and so like, for instance, if her input is actually this coin here, which is the ace 1 in line, she would send like, my input is 0, or like, sorry, my input is like even. And then, and if Bob actually receives that, so he receives that it was supposed to be even, he's going to take all the odd coins and move them up by 1, because they, because then all of those coins would have like, witness corruption if they were actually the correct, her correct input. And then after this, they're going to do it again. So Alice is going to renumber all the coins by their relative rank, and she's going to do it again. So the important thing is that in this protocol is that you can show the following equation. You can show that the positions of the first 3 coins have to, at every point in time, be like at least approximately the number of rounds that have occurred so far. Of course, it's not going to be exactly because, at the beginning of the protocol, a lot of coins are going to linger at 0 for a bit. But as time goes on, they will eventually like, leave the 0 section, and then there'll be like a log n sort of like, loss. So like maybe the number of rounds minus like log n. But anyway, yeah, okay. So maybe the analysis from here will proceed as follows. So because these first 3 coins have to be at least as the number of rounds at every time step, this means that at some point in time, the 3rd coin has to fall off the board, because there's n rounds and the 3 coins have to have position adding up to n. And suppose that it falls off after r rounds. So at this point, you're always going to be sending like either even or odd. So the positions of the first 2 coins, like one of them has to witness a corruption. So these are going to increase by 1 each round. So maybe rewriting sort of this observation, we can rewrite the above equation as follows. The sum of the positions of the first 2 coins plus the minimum of the position of the 3rd coin and n over 3, so like the call for falling off the board, is at least n by the end of the protocol. But then this means that only 1 coin can stay on the board, because if both coins 1 and 2 were at positions less than n over 3, then the above equation would not be satisfied. So this analysis is kind of important. The idea that we're really capturing is like the sum of the first 3 positions of the coins, of the positions of the first 3 coins on the board. Okay, so maybe let's discuss why this isn't so sufficient for our problem. So here are some issues. The first issue is that Bob is sending feedback after every bit. So again, this will mean that he will have to send k rounds of feedback and k bits of feedback. Yeah, and so I guess like, maybe this isn't so hard to solve. Like, you could imagine, for instance, like batching the feedback into like smaller chunks and then having as in many bits. So this is maybe not so much of an issue. The bigger issue is as follows, that Bob needs to send enough information for Alice to know the location of all the coins. So in particular, like he needs to have her know his exact state at every single point in time. And this requires at a minimum, like O of k, like at least k bits of feedback. For instance, he could send like, exactly what he's received at every point, which would tell her his state, but anything less than that would probably not be sufficient to tell her exactly what he has. So that's going to be our main issue. So I guess let's see how we can minimize this, like this number of bits Bob is sending as feedback. So the main idea is, what if we do Spencer-Winkler on only the first O of 1 coins instead of all the coins? So here's the issue though, like sending the identity of the first O of 1 coins is still at least k bits of feedback, right? Like sending even the identity of 1 coin is still k bits of feedback, because you have to send, like what x is, and x is length k. So that's not going to be so good. So we can't even send, like just like even the identity of the first coin. But what we can do is we can send O of 1 indices and the values that the first O of 1 coins take on these indices. And this will be enough to separate these coins into O of 1 like sets. So all the coins, all true to the k coins, into some constant number of sets, S1 up to S O of 1, with a property that the ith coin, where I is in this like little O of 1 of the first like 10 coins, belongs to the set S of I. Okay, and like to communicate this only takes log k bits, because you only have to send a few indices, and then for each of these coins you have to send like the values. So it's like, yeah, and so I guess like the main bottleneck is sending an indice takes log k bits. Okay, so now this is determine a partition of all the coins with like the guarantee that these first 10 coins are separated correctly. And you can play the Spencer-Winkler game on these coins, on these sets now. Okay, and so this is pretty good. So we've solved the communication problem. The one issue with this is that later coins may not move enough. Like before, because Bob was sending his entire state, Alice could guarantee that, like, you really, like later coin, like basically they can sort of guarantee a separation between all the coins because she knows where everything is. But now the issue is that, you don't actually know what all the coins are. You only know these sets. They're very coarse. So lots of coins belong to the set S of 1, but they may, they're not going to move enough. So many later coins. So at first it's going to be like 10 coins, and they are like, you're separating these. That's great. The issue is that, other coins that are in S1 that are much further back may just like start not moving enough over time, and they will, eventually end up at not-enough corruption total. Okay, so to solve this problem, we're going to use a modified Spencer-Winkler on the first O of 1 coins. Okay, so again, like Bob is going to send these like O of log k bits as feedback. I'm just going to determine like these sets. And Alice is going to send one of three things. She's going to send C of x if x is in S of 1, so separating out the coins of S1. And then she's going to send messages M2 and M3 if x is in an even number set, and M3 if x is in an odd number set. And maybe something else I should mention is that between each of these 3 bullet points, these messages are distanced 2/3 apart. Okay, and so this turns out to fix it. You're essentially like, adding distance into the set S1, which is like the problematic set. And so again, as before, you have this this equation that the sum of the first 3 coins is going to be at least at position R after R rounds, which is good. And you also have the following equation, which is that the sum of the position of the first coin, the second coin, and like a large, like sort of just like a far away-ish coin is going to be at least R also. So we fix the problem now, large coins are still moving enough. Okay, and so now with all this in mind, let me describe our final protocol. So our protocol is going to be as follows. We're going to split the protocol into O of 1 chunks, each consisting of O of 1 rounds. And each chunk, we are going to do the following. So if the position of the third coin is very close to the position of a large coin, so a far away coin, we're going to just use the ECC strategy. Because essentially, like, there isn't too many coins that are like, hovering too far away from everything else, which is moving very quickly. So in this case, it's okay to use the ECC strategy. We're not losing very much. The second strategy we use is in the case that position 3 of the third coin is like pretty far away from the position of the large coin. And in this case, we're going to do the modified Spencer-Winkler protocol on the first O of 1 coins. And this will again have the properties as the sum of the positions of coins 1, 2, and large is at least R, but it also separates out the first 3 coins as well. And yeah, okay. And so because we're only doing strategy 1, the ECC strategy, when the third coin is about as far as a large coin, you get the following equation always holds for the entire protocol. That the positions of the first 3 coins add up to about the number of rounds. And that's sort of the magic here. Like, the casework is very important. You are sort of like ensuring that the third coin is always, approximation for the large coin, and choosing which strategy to do accordingly. So the ECC strategy has a benefit that you're pushing many things very quickly. The other strategies, the Spencer-Winkler strategy, has a property that you're actually managing to separate the first 3 coins, but only in the case, but like only when like the large coin is like kind of far away. And so you need to actually separate out these like early coins more. Okay, and maybe let me just finish the analysis now. So the analysis is sort of similar to the Spencer-Winkler analysis we did earlier. We have the sum of the first 3 coins is always about at least number of rounds. At some point, the third coin will fall off the board. At this point, we're going to switch to a strategy separating just the first 2 coins. So the positions of the first 2 coins will increase by 1 each round. This can be done, for instance, by sending 1 if you're in set S1 and a 0 if you're in set S2, for instance. And so then we have the following equation: the position of coin 1 plus the position of coin 2 plus the minimum of position of coin 3 and n over 3 is at least n. This means that only 1 coin can stay on the board as before. And I think that's it. Okay, so in conclusion, in this talk, we looked at error correcting codes as feedback, and we constructed error correcting codes as feedback that have optimal error resilience, but asymptotically minimal feedback. So just a few questions to end this talk with. The first is that throughout this entire talk, we've always assumed that our protocol is deterministic. And so the first question I want to ask is, what about for randomized protocols? So in particular, we believe that perhaps the lower bound that we have no longer holds for randomized protocols. And so the question is like, can you actually construct a protocol with a matching lower bound that does even better than O of log k bits of feedback? The second question I want to ask is the following. So in this talk, we have looked at minimizing the amount of feedback while preserving error resilience. And more precisely, we ask the question of what is the power of feedback in error correcting codes? And in particular, we want to understand perhaps like, the exact trade-off between the number of rounds and error resilience. I want to mention this has been studied, starting with like more precisely in the works of Braverman, Efferman-Cook, Zhang, 2022. They asked the question, if there is exactly, one round or a few rounds, like counts the number of rounds of feedback, what is the error resilience you then get? But you can ask this more general, like for any constant, what is the error resilience you get? What is the trade-off between epsilon? So like, or like, sorry, and asymptotically with epsilon. So for instance, like if you want to get like 1/3 minus epsilon error resilience, like what is number of rounds? Like we showed in this paper that you need at least like O of epsilon 1 rounds, but like what's the dependence on epsilon? And also we asked a question for bits in number of, okay, this is so bad.